Okay, so we're going to continue then on our acid-base lectures, and I'm just setting my timer. Okay. So where we ended at the end of last lecture was with the statement that a strong acid, let's say HA, must be associated with a weak conjugate base A minus. Right? That this must be the case. So here is my acid. This is my conjugate base. Remember the definition of a conjugate base. Well, I can actually use two definitions. I can say that the conjugate base is the species that is formed when the acid loses a proton. It is also the species that functions as the base in the reverse reaction. So when HA, the acid, loses a proton, it forms A minus. Therefore, A minus is the conjugate base. If I'm going backwards, A minus plus H plus, the species that acts as the base vis-a-vis the proton acceptor or the electron pair donor, right? The electron pair donor, that species is the conjugate base. Okay? It's kind of funny how we define conjugate base and base, but it all depends on the direction the arrows are written in, but that's another point. So obviously, if HA is a strong acid, it means the equilibrium lies far to the right. And what that implies is that the ability of A minus to gobble up protons and go backwards is really quite poor. That A minus is a very poor or very weak base. If it's a weak base, it means it's an unreactive base. If it's an unreactive base, it's because it's a stable base. So HA would be a strong acid if and only if its conjugate base is weak. Okay? Similarly, if I tell you that HX is a weak acid, right? What I'm really telling you is that not only is HX not going to generate lots of H plus and X minus, but the X minuses that are generated have a tremendous capacity to gobble up protons and to go backwards into HX. So if HX is a weak acid, it is because X minus is a strong conjugate base. A strong base is a reactive base, right? The reason it's a strong base is because it's gobbling up protons and going backwards, which means it's a reactive base. And if it's a reactive base, it's because it is inherently unstable. So a strong acid, right, a strong acid must be associated, right, it must be associated with and I can pick the adjective, a weak or a stable or an unreactive conjugate base. And all of these words add up to the same thing. Okay? Similarly, a weak acid must be associated with a strong conjugate base or an unstable conjugate base or a reactive conjugate base. Okay? Okay. So it means then that a major factor that affects the strength of an acid, and we've looked at lots already, right? Look, the factors were the solvent, which we talked about. We looked at the HX bond, right? And the third factor really would be the stability of X minus. But we looked at that in terms of the size of X, right? We said that the bigger X is, the more dispersed the electron density is, right? We looked at it in terms of the hybridization, right, of X, because if X were, for example, sp hybridized, the electron pair is very close to the nucleus, and therefore electron pair is stabilized. And we also looked at the electronegativity of X, right? Because obviously if X is electronegative, then it's pretty good at drawing electrons towards itself, which means it's good at handling electron density. But I can say then, really, that the stability of an anion comes down to one fundamental issue, which is how does it dissipate the charge, right? It comes down to how charge is delocalized or dissipated, right? it comes down to charge delocalization. Right? A species can delocalize a charge, and this is where we're going to intersect, by simply being big. That's why I minus was a weaker conjugate base than F minus, because the I minus is allowing the 1 minus charge to be dispersed or delocalized over a large area, so its charge density is low, its stability is high, its greed for a proton is very poor, and therefore it's going to be a weak base. A species can also dissipate the charge by what we call electronic methods. Right? So I can delocalize my charge either by being big or by using electronic means, right? By some electronic factors. And those electronic factors are induction and resonance. Okay? Induction and resonance. So, what is induction? You met this in Gen Chem, and we talked about it briefly also early in 3.1. Induction is electron drift that occurs along a sigma bond. So, for example, when I have C attached to Cl, because the Cl is more electronegative, the electron pair drifts towards the Cl, and that generates a negative dipole on the chlorine, a positive dipole on the Cl, on the carbon. That's induction. So induction arises because of a difference in electronegativity, right? Inherently, because of a difference in electronegativities of the atoms in the bond. So induction is simply electron drift along a sigma bond. Resonance, on the other hand, is also an electronic phenomenon that deals with electron drift involving a pi system. Right? So resonance is electron drift involving a pi system. So understand what we're doing. We said at the end of last lecture, and reinforce it in this one, that a major factor that affects the strength of an acid is the stability of the conjugate base. The stability of the conjugate base comes down to one major factor. How is the negative charge on the base stabilized? And the answer is we can stabilize a minus charge by simply being big. That's the crudest way of doing it, but it's very effective. I know it's effective because HI is a very strong acid compared to HF and certainly and HCl and so on. So imagine that. HCl we call a very strong acid. HI is an even stronger acid than HF, than HCl, because HI has an iodine which is bigger than chlorine. So size is a very, very powerful factor in determining the strength of an acid. Another factor that affects the strength of the conjugate base is electronic factors. And there are two electronic factors that we will consider. One is induction, which is drift along a sigma bond, electron drift along a sigma bond. And the other is resonance. So let's see how these things play out. We defined induction a second ago. Resonance, remember we talked about the resonance condition, right? If I have either a plus charge or a lone electron or a lone pair or a minus charge, a single bond away from multiple bond, I'm going to have resonance. So for example, if I have this, right, I'm going to have resonance like so. And I'll end up with a resonance hybrid that looks like this. Or if I had, let's say I had a carbonyl group here with a minus charge on this site, that will give rise to a resonance form that looks like this. Okay, so I can say that my hybrid looks like this. And I'll have a delta minus charge here and a delta minus charge here. Or if you want, just put a, oh crikey, just put a, so delta minus in this carbon, and a delta minus in this carbon. Or I can simply draw that like so. Bang, 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 until there's a minus charge that's delocalized between them. We can also get resonance, by the way, if I had something like this, right? So if I have O with lone pairs of electrons on it, right? Let's say it's an OR, for example. Okay, then I can also have resonance of this type, okay, which gives rise to this species. Okay, so that's the condition where there's a lone pair of electrons. So what resonance does is it allows the charge to be dispersed or to be delocalized. So instead of having my charge localized on a single atom, I have smeared it among several atoms. Instead of having my minus charge localized on a single atom, I have smeared it or delocalized it over several atoms. So resonance plays a significant role in the stability of any particle, right, that either has a positive charge, a lone electron, a lone pair, or a minus charge. But it's a very interesting feature, a very big difference between resonance and induction. And the big difference is that of the two factors, resonance, by and large, beats induction. In other words, of the two factors, the two methods of charge delocalization, resonance is much, much more effective than induction. So resonance always trumps induction, right? So the question is, why? And the answer really is very simple. Induction involves the drift of electrons along a sigma bond. In a sigma bond, the sigma electrons are held in place by a strong attraction between those electrons and the nuclei, because sigma bonds are the strongest of our bonds, right? So those electrons in a sigma bond are held very tightly. Therefore, they will not respond well, they will not move a lot in response to a potential difference. So if I have H attached to O, yes, the O is more electronegative than the H, right? The O is more electronegative than the H. And the electrons will drift towards the O. But the amount of drift they're allowed is compromised by the fact that the electrons are held tightly in the OH bond. Okay? So induction is present, but the effect of induction is weak. It also turns out that the inductive effect is so weak that it dies off very quickly. So let's say, for example, I put a Cl on this carbon. So the Cl has a delta minus 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 charge. It will induce a delta minus minus, it will induce a delta plus 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 on this carbon, a delta plus plus on that carbon, a delta plus on this carbon, and beyond the third bond, there's nothing. So induction is very strong along the first bond, meaning the electrons have drifted, somewhat towards the Cl. When the electrons in the CCl bond move towards the Cl, it creates a little hole on this carbon. In response, the two sigma electrons here drift a bit towards this carbon, but not a lot. That will create a small hole on this carbon, and in response, the electrons here will drift towards this carbon. But so induction is very strong along the first bond. It is modest along the second bond. It is weak along the third bond, and for most intents and purposes, vanishes beyond bond 3. Okay? So induction is very strong along the first bond, modest along the second bond, weak but present along the third, and for all intents and purposes, 95% of the times, it disappears beyond the first bond, beyond the third bond. So the two salient features of induction are, it is generally a weaker electronic effect than resonance, because induction involves a drift of electrons along a sigma bond. Sigma bonds hold their electrons tightly, with an iron fist, if you will, so those electrons cannot move very well in response to potential difference. The other thing about inductive effects is that the inductive effect dies off fairly rapidly. It's potent along the first bond, modest along the second bond, weak along the third bond, and then pretty much is gone beyond that. In contrast, resonance has two big differences. Resonance involves the drift of electrons along a pi system. And unlike sigma bonds, which hold their electrons tightly, because it's an end-on overlap of my orbitals, pi bonds do not hold their electrons that tightly. So if those electrons are not held very tightly, they are free to respond to potential differences in the molecule, right? To differences in potential. And by that I mean, if there's a delta plus site, they will move towards it. If there's a delta minus site, they will move away from it. So pi electrons are not held as tightly as sigma electrons, so they're freer to move. They can move more freely. And as a result, the resonance effect is much more potent than the inductive effect. Now, I'm just going to point something out. You remember that when we defined basicity and nucleophilicity, we said a nucleophile was an electron pair donor. And which species would confer nucleophilicity? Lone pairs were more nucleophilic than sigma pairs, which were more nucleophilic than pi pairs. And why was that? Lone pairs of electrons are held on the molecule by the attractive pull of one nucleus. Pi pairs are held onto the molecule by the attractive pull of two nuclei, but weakly so. Sigma pairs were way below because they are bound to the molecule by the attractive pull of two nuclei, and they are bound tightly. So sigma electrons are not nucleophilic because they don't come off because they're held so tightly. Pi electrons are nucleophilic because even though they're bound by two nuclei, they're bound weakly. So for that reason, this direction indicates increasing nucleophilicity, right? The ability of the thing to donate electrons, right? It also shows increasing basicity because a base is a species that donates an electron pair. Okay, so increasing basicity. But it also explains the inductive effect, right? So it is also a measure of induction versus resonance, right? So because pi electrons are bound less tightly, they can respond more to a potential difference in the molecule, and therefore resonance is going to beat induction. So that's the first thing. Resonance is more potent than induction. But the other big feature of resonance is, as long as I can have my minus single bond from my pi electron pair, I can get resonance. So I can draw this resonance form. Bang, 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 bang. So I'll have this on a minus charge. But I'll still have a minus charge, a single bond away from a multiple bond. So I can draw this resonance form. Bang, 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 bang. Oh, good Lord. Right? And I can draw this resonance form, and so on and so on and so on. In other words, the resonance effect, not only is it stronger, but it does not die off. So I can say this minus charge is actually localized over this entire skeleton. Now, obviously, what this means is that the area over which this negative charge is dispersed has now increased dramatically. Right? The area over which this charge is dispersed is increased dramatically. And therefore, I have stabilized the species. Because fundamentally, I can stabilize a charged particle by dispersing the charge. And the larger the area over which I've dispersed the charge, the more stable is the species. Okay? So, if, for example, I were to look at a series of acids, let's say I were to look at these acids. So I'm going to compare the relative strengths of, let's say, ethanol, well, I'm sorry, 1, 2, 3, 4, butanol, which I'm going to compare to, say, 2-chlorobutanol, which I'm going to compare to 2-fluorobutanol. And I would ask you, which of these is the strongest acid? Well, you will say, we're going to assume, now of course, what are the factors affecting the strength of an acid? And the factors are the solvent, which unless you're told otherwise, is going to be the same for all the acids under consideration. 2 is the HX bond. 3 is the stability of X minus. So, let's assume the solvent is a wash. The HX bond, for all intents and purposes, is an OH bond, and so we're going to assume that the OH bonds are all equivalent. So the stability or the strength of these acids, the relative strength of the strength of these acids, the relative strengths, will come down to how stable X minus is. So let's imagine what happens when I deprotonate, when I take the proton off, and I deprotonate each of these. That's going to give rise to this conjugate base, and this conjugate base. Alkyl groups are electron releasing. This is something we learned today, and you have to remember this. Alkyl groups are electron releasing groups, right? They're called ERGs, right? In contrast, some groups like chlorine, right? So halogens, for example, right? And in general, halogens or heteroatoms are EWGs. They are electron withdrawing groups. So this alkyl group, the butyl group, actively dumps electron density onto the O minus. Now, not only is the O bearing a minus charge, so the minus charge is on an oxygen atom, which is a relatively small atom, and therefore it's fairly intense, but the alkyl group is actually dumping even more electron density on it. So it means then that this is going to be a pretty unhappy camper, because the charge is not only is the charge not delocalized, it's actually concentrated on the O. So this conjugate base is not going to be very, very stable, and therefore it will tend to gobble up protons and go backwards. And I'd expect this to be an unstable conjugate base, therefore a strong conjugate base, therefore the acid will be weak. Flash forward to this species. I have an O minus, but 1, 2, 3 bonds away, which is within the realm of induction, I have a chlorine. And the chlorine will draw electron density from this carbon, which will draw electron density from that carbon by induction, which will draw electron density from the O by induction. So it means the minus charge on this O is actually bled all the way down here by the chlorine. So in the end, this chlorine is bearing part of the brunt of the negative charge that the O has. So the minus charge is not as localized here as it is here. In other words, it's more delocalized. And as a result, this conjugate base is more stable. If it's more stable, it's weaker. And as a result, this acid is stronger than that acid. So if I use the same, well, I'll have something like this. The conjugate base is a little bit weaker, right? So in fact, what I'll do is I'll draw this as the length of my arrow going forward. So let's say that's the length of my arrow going forward. The length of the arrow going back is going to be somewhat smaller. So my Ka here is larger. Obviously, fluorine is more electronegative than chlorine. So fluorine's ability to draw electrons from the carbon is even greater. This will therefore draw more electrons from this carbon, draw more electrons from the O. So the more electronegative atom is more effective at bleeding electron density from the O, and therefore delocalizing the charge even more effectively. Right? So there's a greater delta minus charge on the fluorine than there was here, which means the charge in the O is going to be less. So as I put the fluorine atom, as I change from H to Cl to F, the acidity of the compound increases. You might expect that if I had had this compound, if I stuck 2 fluorines on, then that's an even stronger acid still, because obviously I'm going to be bleeding tons of electrons. I'll be hemorrhaging electron density from the O minus. Okay, I'm going to make a little point here. And the point is, you could have asked me, why do I not look at the OH bond? And part of my answer was the OH bond will be the same for all the compounds. And that's not entirely correct, because this atom is actually 1, 2, 3, 4 bonds away from the H. And 4 bonds really is a little too far for the inductive effect to be felt. And so I'm going to ignore the effect of the atom at this position. But if I had a case where, for example, the atom were closer, and I can't actually have it for this particular compound, but if I had the halogen atom closer, then, and it was in the range of the H, the 3-bond range of the H, that's my limit, then the OH bonds would not exactly be the same, right? And as a result, those H's become more acidic. So in other words, if I were to look at a compound of this type, and I'm asking what about the acidity of this H, well then obviously a fluorine here makes this H somewhat acidic because we are 1, 2, 3 bonds, and 3 bonds is just in my range, right? Whereas, for example, a bromine would make it less acidic. Okay? All right, so the inductive effect then can play a role in the strength of the acid. Okay? The resonance effect can also play a role if, for example, I were looking at the following compounds. So let's look at the following compounds. Cyclohexanol, this compound is called phenol, and let's look at benzoic acid. So this is cyclohexanol, this is phenol, and this is benzoic acid. So we're going to look at the relative acidities of those 3 compounds. Well, what does the strength of an acid depend upon? It depends upon the solvent, it depends upon the HX bond, it depends upon the stability of X minus. And that has several factors to it, right? That is a matter of size, it's a matter of electronic effects, which are induction and resonance, right? Induction and resonance, and of course hybridization. Well, unless I'm told otherwise, my solvent is the same, a non-factor. The most acidic bond in all of these compounds, obviously the most acidic H in all these compounds, obviously is the H on the O, because the O is the electronegative atom. So they're all OH bonds, so I'm going to assume the HX bond is the same. So the factor affecting the strength of the acid comes down to, again, the stability of the conjugate base. Well, size is a non-issue because I'm dealing with O, right, in all the cases. And if I look, I'm going to consider what my conjugate bases look like. So here is the conjugate base, which is the alkoxide. This is an alkoxide ion. This would be the phenoxide ion. Right, this is the phenoxide. And this would be the benzoate ion. Okay. Excuse me. Well, let's look at the stabilities. Alkyl groups, including cyclohexyls, are electron releasing. So not only am I not going to delocalize the minus charge in the O, I'm going to intensify it. So I'm going to expect this conjugate base to be very, very unstable because of concentrated electron density. It should therefore be very, very reactive, therefore very, very strong. If it's very strong, the tendency would be for it to go back, to gobble up protons and go backwards. Therefore, I'm going to have a weak acid. So I'd expect the alcohol to be a weak acid. The phenoxide. This has an O minus charge, but that O minus charge is stabilized by resonance. It's got O minus, a single bond away from a multiple bond. So I can draw a resonance form like that. I'll need another page. So I can draw resonance forms for the phenoxide that look like this. Okay. My clock is going to alarm, so I'm going to stop it here and then just we just go another 5 minutes or so. Okay. So I can draw resonance forms like so, bang, bang, which will give me this species. I can draw another resonance form, which will give me this species. And sure enough, I can draw another resonance form, which will give me this species. And of course, if I go one more, I'll end up with what I started with. So really then, I can draw the phenoxide as a hybrid, which looks like this. O. There'll be a delta minus charge here, a delta minus charge here, here, and here. Now, just a bit of geography here. The carbon of a benzene ring that bears a substituent is called the ipso carbon. The carbon adjacent to it is called the ortho carbon. This is also then ortho, or O. The carbon 2 positions away is called the meta carbon, or the M carbon. The carbon 4 positions away is called the para carbon, or the P carbon. So ipso, ortho, meta, para. So 2 orthos, 2 metas, 1 para, 1 ipso. So if you look at how the electron density on the phenoxide ion is distributed, it's on the O, the ortho, and the para carbons. There's none on the meta. Now we're all adults. I know carbon is not very electronegative. And while the carbons will share in the burden of the minus charge on the phenoxide, the bulk of the negative charge will remain in the O, because I will apportion the charge such that the atom that is better able to support the charge is the one that has the brunt of it. If I have to carry an 80-pound bag and a 10-pound bag, and I've got a strong guy and a weaker guy, I'll have the strong guy carry the 80 pounds and the weaker guy carry the 10 pounds, right? So if I have an electronegative atom and a bunch of well-meaning but not electronegative carbons, the electronegative O is going to carry the brunt of the charge. Nonetheless, the charge on the O here is much less than the charge on the O here, which is the only atom bearing the charge. And in fact, the other carbon, the carbons in the molecule are dumping electrons on the O. So this alkoxide is very unstable, and therefore it's a strong base. Whereas my phenoxide is actually, a fairly stable entity because of resonance, and therefore it's going to be not a very strong base. It's a modestly weak base, and as a result, the phenols are modestly acidic. Right? Phenols are modestly acidic compounds. Now, one of the things you'll note about the phenoxide is, because I can draw 4 resonance forms, what it really means is that there are 4 atoms, 1, 2, 3, 4, that shoulder the burden of the charge. So basically, the more resonance forms I can draw, the more dissipated the charge is, and therefore the more stable is the species. So as a rule of thumb, the more resonance forms I can draw, the more charge delocalization there is, the more dissipated is the charge, the more stable is the species. So all things being equal, the more resonance forms I can draw, the more stable is the entity. Okay, so I'd expect then phenol to be a stronger acid than the cyclohexanol, which in fact it is. Now, if I look at the carboxylic acid, right, and I've kind of given this away because this one is called a carboxylic acid. When I look at its conjugate base, what I end up with is the carboxylate anion, which in this case is called benzoate. Right, this is the benzoate ion. The thing to guard against is that if you look at the benzoate, you can get really giddy with all of the pi electrons available. But although there's a bunch of pi electrons available, not all of them are accessible to that O minus. Because remember, our condition that's required is that the minus charge be a single bond away from a multiple bond. So I can certainly access the carbonyl group, like so, Okay, I can certainly access the carbonyl group, like so, but I cannot access any of the electrons in the benzene ring, because this minus charge is 2 bonds away from a double bond. That won't cut it. This is 2 bonds away from a double bond. That won't cut it. So the only double bond I can access in this system is the carbonyl group that's adjacent. Now that has a problem, because it means when I draw the carboxylate anion, or the benzoate anion, I draw the hybrid will look like this. Okay? And I'll basically have half minus here and half minus here, but let's just put the minus charge here. So the question is, well, how effectively stabilized is the benzoate ion compared to the phenoxide? Because in the phenoxide, you know, I had 4 atoms shouldering the 1 minus charge. Right? I had 4 atoms shouldering the 1 minus charge. Here I only have 2. And we said that in general, the more resonance forms I can draw, the more delocalized is the charge. And sure enough, the charge is somewhat more delocalized. But in the phenoxide, remember we said that the brunt of the negative charge would be supported by the oxygen, and much less of it is supported by the carbons, because the carbons are not very electronegative. Whereas here, functionally, I have a half minus here and a half minus here. So I'm not going to put a number to it, but you have about maybe 90% of the charge in the O, and the other 10% is dispersed between or among these 3 carbons. So yes, it's a help compared to the alkoxide, but the carbons can't help much. Right? The carbons can't help much because they're not electronegative. Now, had I, for example, stuck fluorine atoms, if I had taken the phenoxide and stuck fluorine atoms strategically on the ortho and para positions, sure enough, the acidity of the phenol would have jumped like a stone, because the ability of the fluorines to bleed electron density from this side would have encouraged the O- to deposit more electron density onto the carbons, because the carbons are being helped by the adjacent fluorines. Okay? But if I look at phenol proper, that is not the case. So yes, I have delocalized the charge in the phenoxide, but it's not as effectively localized as it is in the benzoate. Because in the benzoate, both atoms, although it's only 2 atoms helping to share the charge, both are good at it. Right? Both are oxygens, which are the world's second most electronegative element. So the effectiveness of the charge dispersal is greater in the carboxylate than it is in the benzoate, than it is in the phenoxide. As a result, the benzoate is a much, much more stable conjugate base. Therefore, it's a much weaker conjugate base. And therefore, benzoic acid is a stronger acid. Okay? All right, so we'll stop here, and we'll continue in lecture 3.